Good evening, everyone. Welcome to our today's episode. 26th March is our Independence Day. This year is special because the nation is celebrating the golden jubilee of its independence. Dear viewers, my students, colleagues, teachers, you are watching 60 years celebration of the Department of Statistics, University of Rajshahi, live from my Facebook profile page and Purisankhan Poribar page. You may ask question by commenting. Even if you want to join with our guests, you can easily join by our given link. It is our 20 episode and our journey started from 9th July 2020. Today, we are going to present a special topic on comparison of local power exact test for a common normal mean with unequal variances. And in this special session, our special guest as well as keynote speaker YG Kifle, welcome Dr. Kifle to our today's presentation, and I request you to present your lecture. And this lecture is divided into two parts. In the first part, Dr. Kifle will present his lecture, and in the second part, he will answer the question. Dear viewers, don't hesitate to ask question. So I am really honored Dr. Kifle agreed to join our program, and now I request Dr. Kifle to present your lecture. Dr. Kifle.
All right. Thank you very much. And it's a great pleasure to present our work in this 20th series of online seminar of your department. And I would like to congratulate you also for reaching this milestone of 60 years, okay, of running Department of Statistics. It's not easy. So, yeah, after saying that, I'm going to, share my screen with you. I hope all of you can see this one. All
yes,
right.
You may proceed.
Okay. So, as it is already introduced by the chair of the department, so today my presentation is about comparison of local powers of some exact tests for a common normal mean with unequal variances. And I'm working as an assistant professor in the Department of Mathematics and Statistics of University of Maryland, Baltimore County in the United States. And today's work that I'm going to present is a joint work with Professor B. Malsina, who is my mentor, and our doctoral student, Professor Mr. Alain Molu. Okay, so this work has been already accepted for publication in a special volume dedicated to the birth centenary of Professor C.R. Rao. All right, so what is now the outline of my presentation? So first I will introduce you the background of the problem, and then I will review some of the exact tests available for this common mean problem of K independent studies. Some of them are p-value based, and some of them are just directly using the t-test statistics and the F statistics. And then since we have these different exact tests, we want to compare them using their local powers. So then I'm going to show you how we, come up with the different expressions of local power of these exact tests. Some of them, as I said, p-value based, and the others are based on T and F. And then after coming up with an expression about their local powers, the next step is, of course, to compare them based on those expressions and some values for sample size, the number of studies. And then I will show you a result on the comparison of these local powers. And then I will close my presentation with some general conclusion of the work. So, as an introduction, this problem of statistical inference about the common mean of several univariate populations, which are normal, with unknown variances, and these unknown variances are even possibly unequal. This is, this problem exists already for so long, like you can imagine for the last 70 years, statisticians are presenting in one way or another, addressing this common mean problem. And why this problem is interesting, I will tell you in the coming slides. But in any case, this common mean problem is a special form of, or a special type of statistical meta-analysis. So I think those of you who attended the previous series or seminar conducted by Dr. Sina, you have already exposed with this term, statistical meta-analysis, which is analysis of analysis. But in the next slide, I will show you, the real definition of what is a meta-analysis is. But in any case, this common mean problem is a special kind of statistical meta-analysis problem, in a sense that, in statistical meta-analysis, we have the name effect size. This is nothing but this is the parameter of interest on which we are interested on, that we want to, perform inference on this effect size. This effect size could be what? Mean difference between two groups, maybe control and treated. It could be risk difference. It could be odds ratio. It could be correlation. But when you come to the mean, effect size could also be the mean. But now we're not going to compare different groups. Okay, so what we're going to do is we're going to infer or give a conclusion or perform hypothesis testing or confidence interval about the common mean of several univariate populations. So we have that kind of distinction for this common mean problem. But generally in statistical meta-analysis, you also compare these different groups. So this is the topic of our today's presentation, this common mean problem. But as I said, what is the term meta is? Okay, so this meta comes from a Latin word. Okay, like as you know, as a statistician, what alpha, gamma, beta, and like that we have now meta. Okay, so what meta is nothing but it means beyond, after, or behind, or more. To understand, it's very easy. You can just know meta x equals x about x. If I say metadata, so it's data about data. If I say meta-analysis, it's analysis about analysis. Okay? Or these are, if you say meta-joke, it's a joke about jokes. So this is how you can easily understand meta-analysis. So it's analysis of more analysis. So we do have already published the result on the same goal from different independent studies. So we want to perform a meta-analysis. So we are going to analyze those already analyzed and published results. That's what we call meta-analysis. Okay, meta-x, very easy, x about x. Data about data, analysis about analysis. All right, so now, what are the, when you open any statistical meta-analysis book or some literature, usually you'll find this example. This is a commonly used example in this statistical meta-analysis area. So what this one is, Paul Meyer in 1953 was approached by his colleagues to draw inference about the mean percentage of albumin in plasma protein. based on result from 4 different experiments. So you have experiment A, experiment B, experiment C, and experiment D, and with these different small sample sizes. And then from these samples, then you can calculate the mean. Okay, then for sure you're going to have 4 different means, but you can see them. So these are not like very far apart from each other. These are, revolving around some common mean. Okay, but if you see the variances from each sample, so you'll see, for example, experiment B is 7.8 and experiment C is 33.4. So you can see that this process comes from not the same variance, okay? Then you can see that there is a real heterogeneity here or different among the variances. So we cannot assume equal variance here and maybe perform ANOVA or things like that. That's impossible here, okay? So then he was confronted with this kind of problem. How are you going to then draw inference? That inference could be testing, okay? Like the common mean equals to some value, let's say 60. Okay, how are you going to combine these 4 results, okay, in order to test that kind of hypothesis? That is now the area of statistical meta-analysis. Another one, a very similar one, is also in 1989. Eberhard was approached again to just analyze this result from 4 different experiments about selenium content in non-fat milk powder. Again, you can see the sample sizes. These are small again, and you can see the mean 105, 109, 109, 113. So again, these means are revolving around some common mean. These are not, like very much apart from each other, unlike the variances. If you see the sample variances, even you can have 2 and you can have 85. So are you going to reject those which are not precise, let's say that 85 or 20? Or are you going to take the most, precise one, 2.7? No, you're not going to discard any information. Of course, as a statistician, you need to extract as much information as you can from the available data, yes? So then how are you going to combine this? All right, not only those 2 examples, you can apply this common mean problem in different areas. For example, you might be interested to combine data from several sources that are conducted using different surveys. For example, even environmental data analysis, like, sometimes you can see hotspots. So upon identifying a hotspot in a contaminated area, that the municipality or the county would like to perform a quick analysis. What they do, they take samples, okay, and then immediately simultaneously send out those samples to different labs, and they will quickly get results, okay, from these different labs. So then you want to combine, okay? So how are you going to do that? Even in the, you can apply also in Census Bureau when you want inference about the average wage of, graduates in a certain states, but you have information from county level, yes? So you want to generalize for a county, for the state, sorry. In the US, we have states and we have then county and the like, yes? So then that also applied in this setup in Census Bureau application here in the United States. So you do this kind of also study. So you want to combine. But the thing here, for example, county level variances here are not, the same. These are heterogeneous, but you want to do a common mean kind of hypothesis. So how are you going to combine? So there are different areas upon which you can apply this common mean problem. Okay. Another one is even in the regression context. So in a multiple linear regression where you want to regress y against, p explanatory variables, as you know, now your y will follow normal distribution with this expectation x transpose beta and this sigma matrix, yes? And then what you want, you're going to test this common beta equals to beta naught, like our common mean hypothesis, okay? So like this one, now, in order to test, let's talk about first a single experiment. You want to test beta equals to beta naught. So as you know, you're going to use F procedure. So you can have F statistic, which is a ratio of regression mean square by error mean square. Of course, this follows an F distribution. And then if this thing is very large, then you reject. What is large? Okay, greater than that critical value at certain level of significance. Now, the issue is you're not going to have one study like that. You're going to have k-independent study like this one, okay, about this common regression vector beta. So what are you going to have? You are going to have F1 from the first study up to Fk from the k's population. So then, but your interest is about common regression vector beta. So that means you need to combine all this F, okay? Mind you, so error variances are different across the studies. So we are not going to assume that, error variances are the same. No, these are heterogeneous. So, but I want to perform one overall common regression vector beta hypothesis. So I have to have a way by which I can combine F1 up to Fk. Okay, so then this is the problem at hand. Okay, whether it's regression, whether it's in a survey, whether those the lab experiment. In any case, we are confronted with k different test statistics that we want to combine. It could be even k p values. From this F1 you can get P1. Yes, from this Fk you can calculate Pk. Sometimes researchers reported p values. Then you want to combine these p-values, okay? That's where we're going to use a statistical meta-analysis. Now, let's see, why this common mean problem is really popular still now, okay? As I said, we're going to have k-independent normal populations, okay? Let's say that the i's population follows a normal distribution with a common mean mu, not mu I. Now, I'm going to say that the common mean mu and then a variance sigma square I, because I use I because they are not the same. And this sigma square I is also unknown. So this is unknown. I want to perform, inference on this one, on the common mean mu. So what you're going to do then, you're going to select samples. Okay, you're going to select samples from each of the k populations. Let's say that the i's population, I have a sample of size ni. So I'm going to compute x bar I, the sample, and then I'm going to compute the sample variance, yes? And since, my data comes from a normal distribution, okay, so it's obvious that x bar follows a normal distribution with a common mean mu and sigma square I over ni. Okay, as you can see here, I have one common mean, but this is different among the different studies. Okay, so this now, and then as you know, the ratio of this sample variance by the population variance with this degrees of freedom, this follows chi-square distribution with ni minus 1 degrees of freedom, and this x bar I and I square are mutually independent. Each study, like each pair, is independent of each other. Okay, so now how many sufficient statistics or summary statistics do you have? So from the first x bar 1 and s1 square, from the second x bar 2 and s2 square, like that up to x bar k s square k. So you're going to have what? 2 times k or 2k sufficient statistics. For what? In order to estimate these parameters. How many parameters do you have? You have k here, population variances, and only one common mean. So then, so you have 2k versus k plus 1. Yeah. So you can see mostly, in most cases you have, equal. So you have 2k sufficient statistics for 2k parameters. But because of we are dealing with the common mean, we are not going to have 2k here. We are not going to have k means. No, we are going to have only one mean. Because of this, what you're going to have is, let's say that you want to come up with an unbiased estimator for your population mean. Okay, so if you come, let's say that you come with x bar 1 minus x bar 2. Let's say this is unbiased, yes? So you can add always a zero function to this unbiased estimator. Always, for any unbiased estimator, you can get, you can add a zero function, which is still that estimator is an unbiased. For example, y bar 1 minus y bar 4. If you see this, if you take the expected values of y bar 1 is mu, expected values of y bar 4 is mu. If you take the difference, it's still 0. Yes? Because of this common mean problem, you're going to have a large class, or even infinite number of unbiased estimator for your common mean. So that leads then you're not going to have a minimum variance estimator for your common mean, so which is a problem, okay, in this situation. That's why this problem is so complicated. So this is very important to understand this 2k versus k plus 1, okay, and this lack of completeness, and this is a curved exponential family issue. All right. Now, since you have already the background about this common mean problem, so what is our interest? Let me come back to the inference, okay, or the hypothesis testing about the common mean. As I said, my interest is to test this hypothesis about the common mean, okay? But I'm going, in order to test this hypothesis, I'm not going to have only one t-statistics. No, I do have k different t-test statistics. So this k independent t-test. Okay, based on this, each ti is calculated this, t-test, which follows a t distribution with ni minus 1 degrees of freedom. Okay, then what? We need to combine this. That's why here the question is how to combine the result from k independent t-tests. Yeah. So from the first population, you do have this t1. From the second sample, you have t2. From the third sample, you have t3 and the like. So you have to combine, okay? So what are the different methods by which you can combine these different test statistics? Now, there are exact procedures that I'm going to discuss in detail in this presentation. And there is some asymptotic procedures. But first, I will start with the asymptotic procedures and then followed by the exact procedure. Mind you, these procedures are now in order to combine all these different results from the k independent studies. All right, so let's start with one assumption. Okay, let's say that the k population variances are known. We didn't say that, when we start, we said that we're going to deal a situation by which we don't know the population variance. But, let's start as if we know the population variance, this bold term. This is known. Then life is very easy about estimating for this common mean, mu. You can apply maximum likelihood estimation, and then you can get your mu hat. And this mu hat, ni by sigma square I, x bar I, all these things, because this is known, sigma square is known, this is known. And then you have this. Even now, you can get the variance of your mu hat. So this is ni by sigma square I. So this is the inverse. This is very nice because this is a minimum variance. Because in the previous situation with 2k versus k plus 1, we couldn't get minimum variance, unbiased estimator. We get an unbiased estimator, but it was not minimum variance. Under the normality situation, that fulfilled. And also, without the normality assumption, this mu hat is even best linear unbiased estimator. Okay, so this is best linear unbiased estimator for estimating your mu. Okay, and once you have your estimator with the variance of your estimator, life is very easy. You can use standard Z procedure to test your hypothesis, even to construct your confidence interval. But is this realistic? No, because we don't know the population variance. Okay, let's see what now. We don't know the population variance. So population variances are unknown. Now then you're going to get this Grable-Dill estimator. Yeah, so this one is mu hat GD. Okay, so in the place of sigma square, now we replaced by sigma SI square. Okay, so replace your population variance by the sample counterparts. Okay, this is fine. Still, this is unbiased. That's good. And this is the variance of U hat GD, expected values of this ratio of this term. To come up with analytic solution for this is almost impossible, or it's very, very hard to find this variance of U hat GD. Even in 1974, these two Indian statisticians, Khatri and Saha, even computed exact expression for this variance of GD, which is not that much user-friendly, you cannot implement it, okay? So analytic exact expression for this one is impossible or very hard because of this, yeah? So then we cannot proceed with the inference because you don't have expression for the variance of your estimator, which is mu hat GD. Then what is the next step? Then to go for approximation. Okay, we're going to approximate this variance of U hat GD. Okay, even Mayer derived first order approximation of the variance, as you can see here, Ni by sigma square I times this term with this first order approximation. But you can see that here you have sigma square, yes? We said that we don't know sigma square. So what we'll do is we will replace sigma square by Si square from the, the sample variance, okay? So sigma square I or sigma square J. All right. Now, what about the other possibilities? Even now, Dr. Sina, who's attending our today's online seminar, is also derived an unbiased estimator for the variance of U hat GD following this chi-square identity procedure, and then come up with this term, this expression for the variance of U hat GD. Again, this is an approximation, yes? This is an approximation. And by the way, this U hat GD, for just an notation purpose, we'll use the first variance with number 1, and the Mayer variance estimator will use variance 2, okay? I showed you this already in the previous slide. But in any case, now, that one is without to this last expression we put with the order term. But in any case, now you have variance of 1, U hat GD, which is based on Dr. Sina, and this variance of U hat GD based on Paul Myers, yes? So you can see the difference of the two. It's not that much. You can see here, it's Ni plus 1, here Ni minus 1. So this is very, very close, even though they use different approaches in the approximation procedure, but they come up with a very close, expression for the variance. And the other one is the classical variance. In literature, in statistical meta-analysis literature, you have this. Okay, most people use this one. By the way, what is this part? What is this variance of U hat GD? If you see this part in both the first variance and the second variance term, expression, this is the first term, or this one. Just ignore, because this part is not contributing that much, and then you ignore this part and have the first part. So in many, like in R, there are packages that only uses this part. By default, even some softwares use only this part, okay, at the variance of U hat GD. And the other one, the fourth one, and the last one which is due to Hartung, and this is another expression. So as you can see here, you have 4 different expressions for the variance of U hat GD, all approximations. Okay, when you see the result out of these 4, maybe Dr. Sina has already shown you, it's not that much different. They are very close to each other. That's very good for their agreement. These results are not that much different from each other. Okay, now we have estimator U hat GD, and in any case, we have the variance. It could be the first, the second, or the third, or the fourth. In any case, now I have my estimator together with its variance. So what is the next step? Life is easy, as I said. You can calculate your Z statistics. You have this one. This is your hypothesized value. You have the variance already. And then this follows a standard normal. Then you reject your hypothesis, two-sided hypothesis, if this fulfilled absolute values of Z greater than this cutoff point. Yeah? Or even you can calculate a confidence interval. It's not difficult, as long as you have your estimator together with the variance. Okay? All right. So this is just background. Now, what is the central focus of today's presentation is we would like to critically examine some exact tests for a common mean via the comparison of their local powers. So I'm going to show you what are the exact tests available. So far, I showed you asymptotic results, large sample things. But now we're going to come to the exact test situation, okay? All right, before I discuss about that, let me just show you, just as a revision, what I said, okay? So in order to test my null hypothesis, I'm going to use a t-test statistics for each of them. So I'm going to have t observed for each sample, okay, and then I'll reject if the absolute values of t observed is greater than this cutoff point. Or equivalently, I can calculate a p-value. You know the definition of a p-value, yeah? So you reject your null hypothesis if your p-value is less than your level of significance alpha, okay? Now, in order to study the size and the power of this exact test that I'm going to discuss in the next slides, what I'm going to do is I'm not going to have this as an observed value, but I will take this as a random value and study the property. So this random means this will be what? It's a function of x bar and s. And then my p-value will be also random because of t random here. And this p-value will follow a uniform distribution. This can easily be shown. This follows a uniform distribution 0, 1 under the null. Okay, then I will study, okay, the different tests for testing H0, including the size of the test, the power, and the like, using p random and t random. Okay, all right. So just to revise what I said, I want to test this hypothesis, mu equals to mu naught versus mu different from mu naught. Okay, so I have k different t-test statistics value, t1 from the first, t up to tk from the last. And these are independent because I calculated this from independent studies. These are independent. And all of them are distributed. This follows a t distribution. Are they identical? That will depend on their sample size. If I use equal sample size for all of them, yes, they are also identically distributed. Otherwise, these t statistics are a function of the degrees of freedom, yeah, the t distribution. The same with f, like I showed you for a regression context, yeah, f1 up to fk. So these are again independently distributed because independent samples, and these are all of them are f. That depends on their degrees of freedom. And p1 to pk, yes, these are identically and also independently distributed. Both of them are uniform under the null, yes. All right, now let me show you now these 6 different exact tests. 4 of them are p-value based, namely Tippett, Wilkinson, inverse normal, and Fisher. And the last 2 are directly using the t-values, t-statistics, and f. Okay, and then I will show you first, I will revise what are these tests, how these are performed, okay, their definition. And then after, I will show you the local power expression for these 6 different exact tests. All right, so the first one is Tippett exact test. Okay, as I said, the first 4 are based on p-value. These are p-values are our input for the first 4 cases. Okay, so now what is the Tippett exact test will say here? So we're going to have p1 to pk. Yeah, these are p-values, and these are independent p-values from from our continuous t-test statistics. Yes, and now, as I said, each pi is uniform under the null. Now the question is, whenever you have these k p-values, p1 up to pk, what are you going to do? Order them in ascending order from smallest to the largest. Then you will have this order statistics. Yeah, just this is order. This is the smallest one and this is the largest one. Okay, then according to Tippett, when are you going to reject your null hypothesis? This one. It's very easy. Only take your smallest p-value and compare against this cutoff point. This, you know, alpha, we can take 5%. I know how many studies I have, the number of studies, k. And then if the smallest p-value, okay, if that is less than this cutoff point, then I will reject the null hypothesis. So what that means, I need at least 1 p-value to be less than this cutoff point. Okay, so it's easy, yes. If you in Tippett, what you need to do is order them, take the first one, and reject if it's less than this cutoff point. By the way, this is also smallest p-value means the largest t statistics. Yes, this is also the same in this. You know, you can have also in this Cohen and this statistician in 1984, they do also similar things, but this is exactly the same. All right. So the other one is Wilkinson's exact test. This is a very, a bigger kind of test, which is a generalization of Tippett test. Okay. So this test uses not just the smallest, but the the smallest p-value. Okay. So in Wilkinson, let's say Wilkinson, what we're going to do, let's say that I have k is equals to 4. Okay. I'm going to have P1 up to P4. So Wilkinson order 1 is, now this will be 1. Okay. Wilkinson order 1 means R equals to 1. So whenever you have R is equals to 1, you're going to go back to Tippett. Okay. So what about Wilkinson order 2? That means you need at least 2 p-values to be less than this cutoff point. What about Wilkinson order 3? You need 3 p-values, not 1, not 2, but you need 3 p-values to be less than this cutoff point. Okay? What about Wilkinson order k? So you need all of them, all the p-value to be less than this cutoff point, dr alpha. So finding this cutoff point is not difficult because your PR follows a beta distribution with these parameters, and this is alpha, your probability of type 1 error. Using this, you can calculate your cutoff point. Yes. So this is in Wilkinson, you're going to have different order. Okay. Wilkinson order 1 is nothing but this is Tippett. Then you are Wilkinson order 2, Wilkinson order 3, up to Wilkinson order k, the last one. Okay. All right. So the third one is inverse normal. So as the name implies here, what we're going to do first, before we conduct this test, I'm going to convert each p-value into the corresponding standard normal square. Okay, I'll change this p-value by taking the inverse, okay, like this one, okay? Then I'll change it to xi, and that xi follows a standard normal distribution. Once I have standard normally distributed kind of values, then it's very easy to perform the test, okay? So then you calculate this value, okay, the sum of those standard normal scores divided by the square root of k. If this is less than minus z alpha, of course, then you reject your null hypothesis. And this is also not difficult, easy procedure. Yes. The other one is a Fisher inverse chi-square test. Okay. As you know, as a statistician, there is a connection between uniform and chi-square distribution. Yes. We can use that. And then what we do, I will calculate the logarithm of pi. I will take the summation and multiply by -2. I know this follows a chi-square distribution with 2k degrees of freedom and at alpha level of significance. Yes. So I will reject if this is greater than this cutoff point. Okay. So this is Fisher. So up to now, whether Fisher, inverse normal, Wilkinson, Tippett, all of them we use what? As a starting material, we use our p-values, k p-values, independent k p-values. All right, so the other one is exact test based on modified t directly. Okay, directly we are going to use our t statistics like this one. I'm going to use absolute values of ti because I'm testing two-sided hypothesis, two-sided alternative hypothesis. Yes. So what I will be doing, I will take the weighted linear combination. Okay, what will be the weight? Well, the weight is the inverse of the variance. And the variance of ti is a function of the degrees of freedom. Yes, as you can see here. So if I have equal sample size, then this weight will be 1. Then I'm going to have only the sum of absolute values of ti. But in any case, I can combine them. I can combine the kt test statistics this way, and we'll have a single value. Yes. And then I'll compare with d1 alpha. And if this value greater than d1 alpha, of course, then I'll reject my null hypothesis. Otherwise, not. Here, now the problem is you don't have a ready-made distribution for this weighted linear combination of the absolute values of ti. So yourself, you need to simulate the values of d1 alpha from this. Yes. So in application, d1 alpha is computed by simulation. All right. So similar, because of this relationship between f and t, like, I can also combine the f, like as I showed you for the case of linear regression. You have k different f values, yes? You can combine like this weighted linear combination. And then you reject your null hypothesis if the sum of this is greater than d2 alpha. Okay, again, this f, the weight is a function of the variance here, and the variance is the function of the degrees of freedom. Okay, and if you have equal sample size, the weights will be 1. Okay, and then this d2 alpha is also obtained by simulation, because we don't have a ready-made distribution for this one. We have it for f, but not for the weighted combination of the fi's. All right, so far we have these 6 exact tests, 4 of them p-value based, 2 of them directly using t and f. So the question is, I want to rank them, at least I want to compare them, in, so that at least to use one of them. So how I'm going to do that? So in this paper, what we did, we tried to compare them based on their local power, based on the power of detecting a very small difference between hypothesized, the null hypothesis and the alternative hypothesis value, which is delta. So for small values of that, how is the power? Okay, that's the local power. All right, so here in this paper, as I said, we derive an expression of the power of the test under the alternative delta. What is delta? The difference between mu minus mu naught, this common mean minus hypothesized value. Okay, and this is different from 0, and we carried out its Taylor expansion around delta is equals to 0. Okay, we only perform this expansion under around 0. That means not for large values of delta, but for small values of delta. How is the power of the test? Okay, since we are dealing with a two-sided test, okay, like this, different from two-sided nature of the test, when we do this Taylor expansion, the first term vanish. Okay, and then you're going to end up with order of, delta square, delta raised to 4, delta raised to 6, and the like. So I'm not going to keep those higher order terms, because delta is already very small. When you take delta raised to 4, you can imagine it will be very small. So the contribution is very negligible. So we keep only the order of delta square. That's why this method that I'm going to discuss, the local power expressions, only work for the local power. When you have large delta, no, that will not work, because we already take it out higher order term like delta raised to 4, considering that delta is very small. Okay, and then now I will show you final expressions of this local power. If you'd like to see, the proof of this all expressions of local power, you can see the published paper. Otherwise, today I'm going to show you only the final expressions of this local power in 2 situations. First, general case for unequal sample size. That means each study do have their own sample size, which is different from each other. We don't assume equal sample size. Then the second one is a special case. Let's assume equal sample size throughout. Okay, and then that will be a special case. But mind you, when I show you a result in the special case, whenever I use psi, this is nothing but the sum of 1 over sigma square I. Okay, I will show you also in the expressions. So step by step for each of these 6 exact tests, now I will show you their local power expressions, one in the general case and the other one is in a special case. All right, so before I go to the expressions, we have this very relevant lemma that we used for most of the p-value based local powers. As I said, this is our alternative hypothesis, alternate hypothesis. Delta equals to is different from 0. Okay, so what we do here, the probability of p greater than c given h1, okay, given h1 is true. We didn't reject the null given h1 is true, and this can be approximated by 1 minus c, okay, which we change c in the different tests. I will show you, we replace c by different terms in the different tests, plus n sample size, okay, and n square delta square over 2 sigma square by psi nu c. Okay, what is psi nu c? So this psi nu c is nothing but the integral of minus t nu up to t nu c by 2, which is the second derivative of this non-central t PDF, with the non-centrality parameter of delta. And when you solve this one, you can get this expression. So we use this expression a lot in deriving the local power of the p-value based tests, most of them. Okay, and you can easily show that this sinus is always less than 0. Okay, so this is the lemma, but now this is the first expression for tippet. Okay, so this is, as I said, the final result. So this is the first one is in a special case. No, this is a general case and this is a special case. Okay, so why I use different color, I will show you. Whatever you see always in blue is common for all tests. Okay, so now for the general case, it's alpha plus delta squared by 2, 1 minus alpha, k minus 1 by k, and this term. You know, now here sin nu I. Now this is tippet. In the place of C, I used now A alpha. What is A alpha? This is the cutoff point for tippet. Okay, so that's why that general lemma helped us in, you know, coming up to these different expressions. And this is the general case. If I assume equal sample size, as you can see here, n can be, you know, this will be common. It can come here. You can see it here. So, and this sin you see also will not anymore depends on I, yeah, because this is equal sample size, then you can take it out like that, just without I. Okay, you are remaining what? 1 over sigma I squared, this sum. That you have it here as psi. Okay, and this is a special case, a blue term, and this is a general case for tippet. Yeah, how you can calculate these different values, you can see it here. And the other one is Wilkinson. For Wilkinson, the local power, again, this blue term and this part, yes, this part here. And again, when you have special case, what you do is you take n out, okay, you have this anymore not depends on I, so you have this here, and in the place of C, by the way, here you use dr alpha, which is a cutoff point for Wilkinson, the one I showed you already, yes? And you can always see that whenever you use r equals to 1, you can immediately go back to your tippet, yeah? And the third one is for inverse normal. For inverse normal, again, you have this blue term here and the other one, okay, the black part. And for the special case, you have this blue term and these values. Okay, for the interest of time, I'm not going to go to each of these parts, but all of them can be easily, you know, computed. Like this is not a nu is nothing but this is expectation of u and q nu. So using this one you can get, and b is nothing but the expectation of u square times q. Okay, what is q? You have this, and yeah, so it's not difficult to calculate all these parts, yeah. And the other one is local power of Fisher. Okay, again you have this blue term and the black term here, a blue and black component here. Okay, as I showed you, again, all this can be easily computed using these expressions. And local power of tippet, again this blue term, and you have this one. Okay, by the way, when you have equal sample size, this way it will not be anymore, you're going to have like that, yes. And when you have equal sample size, whether you use T1, T2, Tk, it's all the same, yeah. So I mean, you're going to have the same distribution anyway, okay, with that common degrees of freedom, n minus 1 for all of them. So this is expression for T1. Expression based on F, local power, again, you have this term. Yes, and then when you have equal sample size, as I showed you, the weights will be 1. You have like this indicator function times this, and then you take the expectation under the null, and then you have this blue term in both special case and general case. So I showed you a lot of expressions. So now in the next slide, what I'm going to do, I will collect them so that I can show you. Okay, so this is now comparison of local powers in a special case. First, let me show you for the special case. Okay, tippet, Wilkinson, order R, inverse normal, Fisher, like T1 based on T, T2 based on F. Yes, so then as you can see here, now you have this blue term, which is common in all cases. Okay, what is the implication of this one? What's the implication? Now, I can compare all of them. The idea is I don't want with the absolute, the magnitude of this local power now, but I want to compare them. I want to rank them based on local power. So for that, what do I need? Do I need to know this psi? What is psi? Psi is a function of what? The variances, yes? This is the sum of 1 over sigma square I. So do I need to know that in order to compare them? No, I don't need that, because I can compare them only based on these black parts. Yes? Okay. And do I need to know this delta, the n, for example? Yes, n is also here. Here, this sin you see is also a function of n. Yes, you need n. Do I need k? Yes, I need k. Other than that, that's very important, because you don't know the population variances. Yes, that's what we said. And I don't need to know them, like in order to compare them, this different exact tests based on their local powers, mainly in the special case. Okay, what about in the general case? Let me take you also that. I will show you to the general case. First, let me show you the result, okay, for this special case. So then we can calculate their local powers. This only I'm going to use the black part, not the blue part, okay? So for that, I need, of course, k, and I need, of course, n. Yes, so you can see, for example, for k is equals to 5, n 15, n 25, 40, and then the like. Okay, you can see throughout modified f and modified t are doing better. So these are doing better when we compare these 6 different tests. And among the p-value based ones, inverse normal is doing good. Okay, in terms of this part, the black part that we compared. Yes, so like modified f and modified t tests, fare the best uniformly in the design parameters n and k. Yes, and Wilkinson test of some r greater than 1 always outperform t-pit, because Wilkinson is a generalization of t-pit, as you can see here. But now you can ask that Wilkinson k is 5. I can have Wilkinson order 1, order 2 up to order 5. Which Wilkinson, which order do I use here? Okay. Now, if I use order 1, of course, I will get t-pit. If I use order 2, which one did I use? I will show you here. Okay, for Wilkinson order, k is equals to 5, I can get different order, yes, 1 to 5. You can see here. So r is equals to 2 is giving you relatively better among others. So this is good, Wilkinson order 2. What about for k is equals to 10? R is equals to 3. For k15, r is equals to 4. You can see roughly k equals to, r equals to root k. Like square root of 5, 2 point something, square root of 10, 3 point something. So you can see that. So that's why I showed you here. If you see this value 0.0633, you'll see it here. Okay, so this is order 2. When you come to k is equals to 10, 0.0412, this one. Okay. All right. So what about for the general case? Okay. For the general case. Now, for the general case, the common terms I have is now reduced, because I'm not going to anymore assume equal sample size. So then also I'm not going to have any more common Yehenew. Okay, so because of that, now I'm going to have only these common terms. Again, I can compare them, okay, without this blue term. What do I need then? I need, of course, the different sample size. I need to know now the population variances. I have to here, I need this as an input in order to compare them in the general case. Let me show you one table that we did. For k is equals to 2, different sample size. I need now the variances. For k is equals to 3, the different sample sizes with their population variances. For k is equals to 4, as you can see, I cannot go for k is equals to 10, because for k is equals to 10, I need n1, n2 up to n10, sigma square 1 up to sigma square 10. So it will be too much here. But in any case, with these small k values and different sample size, then we have seen still modified f is doing better, f followed by modified t. Okay. All right. So now this one is the real local power, not like the coefficients. Okay. But now including those common terms, the only thing I did here, okay, the only thing I did here is I use psi equals to 1, the sum of 1 over sigma square I, because I'm using this part here, this. Okay. When I do that, I need also this psi. Okay. I have n. Now I'm going to use delta square, and you'll have this graph. As you can see here, for your delta, okay, we are not assuming like from 10 to 10. No, it's impossible, because this is local power. We did our Taylor expansion around delta 0. We cannot go far away from 0. We have to stay minus, in the vicinity of 0. And as you can see here now, for alpha 5%, you can see here modified f followed by modified t, and then inverse normal. Okay. And this is for Wilkinson. K is equals to 5. As I showed you, square root of 5 is 2 point something. So R is equals to 2 is the largest here. Okay. So now, what is the conclusion out of this work? As you have seen, in the special case, we can perform a uniform comparison of local power irrespective of the value of the unknown variances. I don't need to worry about the unknown variances. I can compare them without knowing the variances. But mind you, that is for the special case, equal sample size case. And in that case, as you have seen, both in the table and in the chart, in the plot, modified f and modified t test performs the best throughout. Okay. And we have seen also for an equal sample case, even, with limited computation, with small k, we have also seen that the superiority of both modified f and modified t tests compared to other exact tests. So this is the end of my presentation. These are some of the references of the paper. Okay. So thank you very much for your attention to this talk, and this will be the end of my presentation. If you have any question, you are welcome.
Kifle. Yes, thank you, Dr. Kifle, for your nice presentation. But first, I request Professor Bimal K. Sinha to open your video that our students may watch you.
Hello.
Yes, sir. Now I introduce with you Dr. Bimal K. Sinha, Presidential Research Professor, University of Maryland, Baltimore County, USA. Actually, he was presented from the very beginning, and he joined from A to Z. And now first, I ask you, Dr. Bimal Sinha, would you please about something about this presentation?
Okay, now this presentation a bit technical, but since you are already familiar with what I did probably about a month back, so you can see the connection. So we are comparing different test procedures. What I showed in my presentation, we are looking at the confidence interval for mu based on some asymptotic procedures and exact procedures. But this part is we are comparing various test procedures for testing about the common mean mu. But you know that when you have so many test procedures, why? Because we don't have any uniformly most powerful test. Because this is a very very complex scenario in terms of number of sufficient statistics, which is 2k, more than the number of parameters, which is k plus 1, and that leads to all sorts of complexity. So we don't have any best test. So that's why people over the years, they derived whatever they could do, and whenever there's an idea to derive an exact test or an approximate test, immediately you compute the power and you compare with the existing test procedures. But the main idea here is, because we do not have any uniformly most powerful test, that means for all alternatives, you don't expect a test which will have the maximum power. No. What we are looking at here is a very nice idea, because it's always very difficult to distinguish alternatives which are close to the null. If I'm testing 0 against 10, it's not a problem at all. I can give me the data, I can immediately tell you whether the mean is 0 or the mean is 10. But suppose I'm testing 0 against 0.5 or 0 against 0.1. It's so tight, the alternative, That's what makes it extremely difficult. So it's good to know what are the test procedures, among whatever we have, which one will have the maximum power locally. That is the idea here. So local power should be a maximum. Okay, that's the derivation of the local power. That's the theory part. Then we are comparing these various test procedures. Okay.
Thank you, Professor Dr. Bimal Sinha, for his nice explanation. Actually, it's a little bit difficult for our students because it has a very more huge mathematics as well as some technical terms. So actually, a little bit difficult for our student. But some guests are present. Especially, I want to thank Professor Mir Masumali sir from Ball State University. He is really very encouraging for us. And just a comment for you, sir. Nice to see you, Bimal Alida. Another one, Neil Agarwal. Thank you for the presentation, Dr. Kifle. Another postdoctoral fellow, maybe from Japan.
Oh, wow.
Mamunur Rashid. Thank you, Dr. Kifle, sir, for your informative presentation. We are really grateful to you for participating in our program.
Thank you.
Dr. Premananda Bharati from ISI Kolkata, great.
Oh, wow.
Another comment from Mir Masumali, enjoying the presentation.
Thank you.
Another one, Imran Loskor from Rajshahi University, wonderful program, sir. Anicha Farhana, thank you, sir, for your wonderful session. Dr. Kifle, it goes to you.
Thank you.
Thank you, sir, for your nice session. So many comments, actually, but I selected very few comments for you because we are at the end of the program, actually.
Okay.
Another one, Professor Rahmat Limon from Ball State University. Welcome, Dr. Kifle, to our Rajshahi University Statistics family, enjoying our presentation, enjoying your presentation. And so many comments. Another comment from Dr. Saidur Rahman, enjoying this presentation. Hope this session will be very successful. These are the very comment from the very beginning. I hope this session will be great. And so many comments. Good evening, sir. Okay. I want to thank Dr. Kifle for your nice presentation and for your time. That we are very delighted to inform you that when we will arrange our international conference in the next year, maybe, then we will invite you to our university, and hope you will obviously come to our department.
Thank you. Thank you very much. Yes, thank you.
Yes, that will be good.
So I again thank Dr. Bimal K. Sinha for encouraging us and Dr. Kifle for this nice presentation. I want to say goodbye. So thank you, dear viewers, for this to watch this presentation. Thank you, everyone. Good night.
Okay. Thank